Hello everyone. In this video, I'm gonna give a deep dive to Cyberbrain and show you how it works. So this is the poster that we will show in the PyCon poster session. So it has a very high level overview of how it works. So I will first cover how it works from the very high level, and then dive into each step. So maybe first I'll give you a quick demo of Cyberbrain, but I'm sure that you should be able to see that somewhere. So as you can see, we use Cyberbrain to trace the execution of Python of a Python program. So you give it a decorator called trace and run it. We'll show a graph on the right side. So in this example, I have a very simple example, just 3 lines, and it generates a very simple program. So as you can see, we generate a variable c from the input a and b, and then we return c. So that's how that's the program. It's very simple. So I'm gonna show you how this whole thing works from behind the scenes. Okay. So the first step is the source code of the program. And for simplicity, I will only show how c equals a plus b is turned into a graph, and we'll ignore the other steps. So in essence, Cyberbrain works by bytecode tracing. So you know CPython is like runs bytecode under the hood. If you don't know that, go check out the documentation of CPython. And basically, we trace the bytecode that's being executed in the program, so we know what happens in the program. So this is the second step. And I have a video to show you how that works. So this video is the talk I gave at PyCascades this year. I would recommend go check it out. It's a overview from a user's perspective to the project, and it also explains why I made it in the first place. So I'll just play the video.
How do we pull the information out of the interpreter? As you can probably imagine, the interpreter knows all this runtime information. It knows everything that happened in execution. And this information is actually baked into the bytecode. And we'll see what that means. So bytecode, so Python is an interpreted language. What that means is it is not compiled into machine code, but interpreted along the way. And bytecode is what's get interpreted. So if you use the this module, you can see that c equals a plus b actually consists of this bytecode. And we'll explain what that means in the next slide. So to understand the bytecode, we have to learn a bit more about the virtual machine. So CPython's virtual machine is a stack machine. What that means is CPython uses a stack to do all the computations. So at the start of the program, the stack is empty, and then we encounter the first bytecode, which is load name with an argument a. And what it does is it loads the value of a into the stack. So the stack now has a value, which is the value of a. And next is load name b. It does the same with the first the load name a. So now stack has 2 items. Next bytecode is binary add. What it does is it pops the 2 items from the stack, adds them together, and put the result back. So now there's 1 item on the stack, which is the sum of a and b. Finally, there's this bytecode store name c. It pops up the item on the stack and assigned to c. So that's how C equals A plus B is executed on the bytecode level. So we know what this bytecode does, and how do we use them for debugging? To do that, we use an API called setTrace. So what it does is basically you give setTrace a callback, and you can let the callback be triggered every time a bytecode is executed. So here, since there are 4 bytecodes, and the callback will be triggered 4 times. So from the callback's perspective, it see that load name A is called, load name B is called, binary add is called, and store name C is called.
Okay, so that's basically it, and we can take a look at the API, the setTrace API. So if you go to the documentation of the Cs module, you can see that it has a cs.setTrace, and we use the Opcode event. So it supports multiple events like call, line, return, exception, and basically it controls what gets triggered. So we use Opcode, which means that whenever an Opcode, which is bytecode, gets executed, and our trace function, which is just a callback function, gets called. So you can see that the interpreter is about to execute a new bytecode, and the local trace function is called. So let me show you what the code looks like. Let's see. So in the Cyberbrain subdirectory, go to the tracer file, and yeah, so you can see that we call setTrace here. But what's the most interesting part is in the bottom. Basically, we have a bunch of different processing, but in the end, it calls this local tracer function. So this local tracer is the trace function here. So the local tracer will receive a frame object, which is the current frame. So if you don't know what a frame is, it's basically a call frame. So whenever Python calls a new function, it generates a new call frame. So that's what it is, and the frame can persist a bunch of different information. And there's this event. Event is just a string that shows what event it is. So we care about opcode. So and if it's an opcode event, it will go this route. And argument in this case is none. So the opcode event is the most interesting part. So we'll dive into that. And so we have a bunch of different processing with the event. Basically, we look at what the bytecode is doing, and we record all its operations. So it's shown in this graph. This is a very high level overview of the code. So like shown in the video, we know that there are 4 bytecodes gets executed, and we know what they're doing because we understand the meaning of each bytecode. So and in this case, we know that like this is loading A's value onto the stack, and A's value is hello, and also this is loading B's value, and B's value is world, and this one pops the sum of A and B, and this one assign the value that just gets popped to C. So using this information, we can form a very simple graph here with C as the output node and A and B as 2 inputs. And we also know what their value is. And this information is in this file called value stack. So if there's one file to look at in Cyberbrain, that's this file. It is the core of Cyberbrain. So I'll give a very high-level walkthrough of it. So we have a base value stack, and so basically, so this file, this method is that gets called every time a new bytecode, which is the instruction. Bytecode and instruction we are used interchangeably in the project. Like whenever a new bytecode is executed, and this method gets called. And we have a function for each bytecode operation. So like I said, so here the unary positive has a handler, and unary negative, unary not, all has one. These are the bytecode that CPython has, and basically we have a handler for each bytecode. This allows us to track what they're doing and persist all the information that they generate. So, for example, we can track how many elements are left on the value stack and things like that. And these are just the handlers for the bytecode. So we have a Python 3.7 value stack, which is a derived class of base value stack, because as you might imagine, the bytecode in each Python version had some subtle differences, and to be able to handle these differences between different Python versions, we use different subclasses. So Python 3.7 value stack handles the Python 3.7 specific stuff. Like if you know some internals of CPython, you might know that this bytecode has been removed in later versions, and it only exists in 3.7 and the versions before that. So all these things should be handled separately. And we have a Python 3.8. We have a Python 3.9. So that's the basic structure of the value stack file. And so let's go back to this slide. So suppose we already have a graph like this. How do we how do we display this information? How do we visualize it? Because in the end, what you see is a graph, not some random bytes in memory. So we use VS Code to do that, and VS Code gives us a Node.js environment and also a web view for us to basically visualize things. So so step 1, 2, and 3 happens in Python, and step 4 and 5 happens in VS Code. So let's look at step 4. So from step 3 to step 4 is doing RPC communication, basically sending the tracing information to VS Code, and more specifically to a express server running in the Node.js environment carried within the VS Code environment. So let's first look at where it's sending the data. There's a file called rpcclient.py, and if we scroll down, we can see that we have a request post call, and this is just posting to localhost because right now we assume that you run your VS Code editor locally, but in the future we might change this behavior to allow things like remote debugging. And this is just posting what we have, and frame data carries the tracing information, essentially the graph you just saw. And okay, so we now look at the Rpcserver.ts file. This is in the Cyberbrain-VSC folder. So this is basically just a very simple RPC server. Well, actually HTTP server that listens on a specific port. So yeah, it has a handler -frame, and it gets the message that's published from the Python world, the Python side. Okay, so this is step 4. Step 4 is very simple. Now we need to think about how do we pass the information to WebView, because this is a Node.js environment. It's not a WebView. Luckily, VS Code has a built-in mechanism to support that. It's just a communication mechanism. So we go back to the Rpcserver.ts file. We can see that this line, WebView panel.webview.post message. So this is just posting the message that we get from Python to the WebView, where we eventually display a trace graph. So request body is the data we need. So this is the line. And let's look at where WebView receives it. So actually not here. It's in the file tracegraph. Okay, so tracegraph is the file that handles all the visualization. Let's see. Okay. So here we can see that we have a window at event listener, and this listener is listening for the message published from Node.js. And okay, so event.data is the data we need that can help us show the trace graph. So we render a trace graph from it, and all this code in the render function is handling visualization. So I won't dive very deep into that. So on a very high level, this is how Cyberbrain works. Of course, there are a lot more details under the hood, but I just hope you understand one thing, that Cyberbrain is not static analysis, but runtime tracing. And more specifically, it's tracing the bytecode of Python.